Actually, okay.
All right. So good afternoon, everyone, and welcome to this inauguration of PhySeekSee 2021-22. I officially welcome you all on this fine Friday evening. We have here with us the entire Department of PG Physics of St. Joseph's College, Bangalore. Without further ado, I'd like to call Arun sir to welcome us all officially to this meeting. Arun sir.
Thank you, Vikrant. Good afternoon to everyone here. It gives me great pleasure to welcome all of you to our inaugural session of the PG Physics Association. We have named it PhySeekSee. The name is a take on the Greek alphabets Phi, Psi, and Psi, pronounced in the Indo-European manner. Hearty welcome to Dr. Cijy Mathai. Also, a special thanks to her for agreeing to the talk at a rather short notice. Welcome also to Father Roshan, who will introduce Dr. Mathai to you immediately after me. I will quickly finish my part. Just wanted to take a few moments here to reminisce on the association and its current activities. The association started in 2017. However, even before that, the department used to conduct activities as part of imparting a holistic experience to the students. The idea being that in addition to academics, such activities help students to learn leadership and organizational skills. Typically, such activities involved having intercollegiate fests, science exhibitions, etc., in addition to regular visitor talks to inspire the students into higher studies. In 2017, we brought all of these disparate activities under one umbrella and gave a larger control to the students to plan and organize them. Every year, we have been having a special guest speaker inaugurating the activities with a physics talk. This year, too, we have a wonderful speaker and a wonderful topic at hand, hybrid on a topic being hybrid quantum systems. Throughout these years, the leading light on the activities of the association has been Ms. Parul Goel, the coordinator of PhySeekSee. She has a special talent of inspiring and motivating the students to organize interesting events. This year, the following students are in charge of various portfolios. The president of the association is Mr. Vikrant Pulamati, whom you heard just a while back. Vice president is Ms. Shivani Nair. The secretary is Ms. Jalak Mehta. The treasurer Ms. Cijy Fiona Mary. We have a couple of spokespersons in Ms. Srijaya Karanta and Agnes Rajiv, and a creative head in Ms. Alina Maria. The activities of PhySeekSee are highly encouraged and supported by the college through the head of the Department of Physics, Professor Maria Saharaj, the Dean School of Physical Sciences, Professor Rabai Akiba, the Registrar, Professor Melvin Colasso, and the Principal, Reverend Father Dr. Victor Lobo, and also my colleagues, Father Roshan, Ricky Wilfred, and Mohan. I extend a hearty welcome to all of them. Once again, a hearty welcome to Dr. Cijy Mathai for gracing the occasion of the talk, and to all of you in the audience here today. Thank you. Over to you, Vikrant.
Thank you, Arun sir, for that very warm words of welcome. I now invite Father Roshan to introduce our guest speaker. Father?
Yes. Thank you, Vikrant. I have great pleasure in inviting Cijy Mathai for this talk. On a personal note, Cijy and I were classmates for our master's course in Christ University, after which she joined IIT Bombay for a doctorate. And then she went to Israel for a postdoctoral research. I think this is her second postdoctoral research in Israel. And I thank her for having accepted my invitation, our invitation to join us for this talk. Thank you, Dr. Cijy. Welcome for this presentation. Now over to you.
Thank you.
We are all ears to listen to you.
Great. Okay. Hi all. Good afternoon. Yes. It's Israel here, and the time is 11:30 a.m. here. So actually, first of all, let me thank you all, especially the organizing committee and of PhySeekSee. What a wonderful word, PhySeekSee. PhySeekSee, like, you know. So what I will I interpret from that word is like there is that that word itself has some sort of purpose, like, of giving the important, giving value for the word, like seeking physics or seeking truth, seeking knowledge. So that's the sole purpose of this subject itself. So I hats off to that whoever has given the name, and I wish you all the luck for this organization as well. And yes, I take this opportunity to thank Dr. Father Roshan Gasolino, our beloved brother Roshan. He was brother, and then we were friends, classmates, and masters in physics, as he already told, in Price College. And it was wonderful, it was wonderful years there, and he with this wonderful, beautiful, smiling and laughing aura, he gave us beautiful memories over there. So thank you, brother, for calling me and inviting me to this group. And yes, okay. So let me start today's talk, So brother was actually asking me to give a name to this, to give a catchy word, Cijy, give a catchy word to this talk. When he told me that, immediately what came into my head is like, I was not able to understand the nature of the talk. And I just gave him the word, like hybrid quantum systems, based on ferrimagnetic resonators. He told me, "Cijy, give me something, something lighter." I told, brother, I do not understand this word, or okay, the lightest word, it's couple and harmonic oscillators. Yeah, so those are the words which I have given, but then I understood, that's not the right thing which I should, when I thought about it yesterday, I thought, that's not the right caption which it should be. This should be the catchy word, catchy caption. And that is, there is plenty of room at the bottom. This is one of the captions which has been put forward by our doctor, beloved Dr. Richard Feynman. Everybody will be studying his subject, his textbooks and all. So Richard Feynman, he gave this quote in one of his one of the conferences at Caltech. And what he meant by this is okay, next slide will help probably. Yes, we are curious Homo sapiens actually, and we always have this curiosity to learn about the world we are in. And once we almost understood about the world, a little bit, understanding about that the world we are in, the earth, and then we started to look up above. We started to see poetically also, twinkle twinkle little star up above the world so high, and all those things. And we started learning about it, astro world, that's what we call, and Copernicus, and those scientists' names are not coming into my head now. But then those scientists, they started, giving equations to the each and every phenomenon which is happening. The Kepler, right? Kepler. I think Kepler's laws, 3 laws, it's elliptical in nature. Solar systems, the every celestial bodies that will be rotating around one particular system, and elliptical. All these things have been given, importance, and given physical equations to it. And then we started looking, once we started getting an understanding, a little bit better understanding about the astro world in the 17th, 16th centuries and all. And then came the 19th century, where we started to look on, what are the, let us go to the downside, what is in the bottom, what's it in the bottom, they started Rutherford, all these guys started learning about, telling about, atoms. They had the curiosity about learning these small stuffs, they started telling that it's like electrons in the atom is like cherry in a what is it, bacon, something of that sort. Cherry the cake. I'm sorry. Okay, so yeah, so Pauli, Albert Einstein, all these people started giving more importance to the nano world as well, and which I've been into. So there is, all these are because of the curiosity which has been developed in among the among Homo sapiens. So here, my research is mostly focused on into the bottom side of it, that is the nano world, and I mostly work with nano systems. Brother Roshan has, friends who is working in astrophysics as well, and I hope that they will also be invited in the following days. So yeah, so let me give you a little bit understanding of my field of research, what I have been doing. My sole purpose of this talk here is not to give you more technical details and or something. It's just to give you, if I can give you a little bit spark of, to take that textbook which you have and have to get, if I will be able to connect you with, connect your whatever you're studying now with my kind of field of research, then I think my purpose will be done. So that's what. And yeah, so what is my field? My field of research is, I'm basically a quantum physicist. Quantum, we focus on quantum engineering, qubits. Qubits. What is superconducting qubits? What are qubits? Qubits are basically quantum bits. You may be knowing about bits. They are binary digits, and we are very much using those technologies now itself. Now, when we are talking, it also like what is happening is like these whatever signals which I am producing, these audio signals, it is being converted into bits, binary digits, zeros and ones, and those zeros and ones are getting converted to optical signals, and those optical signals to telecom wavelength line. It's reaching from this part of the world, Israel to India, and then again the deconversion process, analog to digital conversion, digital to analog conversion process, and then analog to digital. And after all these processes is what why you are able to listen to me, like so fast and so clear. Yeah, amazing leader. So this bits, binary digits, which are in zeros and ones. So we have this. We wanted to we wanted to upgrade it and use a little bit of quantum aspect in it, and that's what qubits are all about. So qubits are systems where it's not only zeros and ones, the states, which we call it states actually. It's not only zeros and ones, but there are superpositions of these states as well. So superpositions, so it will be a combination, like 50% zero states, 50% one state, or 60-40, that kind of percentage combinations will take place. And along with the zeros and ones kind of communication exchange, information exchange will be able to carry information in the form of these superposition states and states as well. And that is one of the advantages of studying my field, like which is quantum computation and quantum communication, everything. So shown in this image is actually it's a same image of an air bridge. It is something related to qubits, like we are trying to. So qubits are basically qubits based on superconducting superconducting circuits are based on Josephson junctions. You may be knowing about it. Josephson junctions are not semiconductor, superconductor, insulator, superconductor, stacks of that. And the insulator section, it should be as thin as possible, so that we can have some kind of quantum tunneling process which is happening, and the tunneling of the particles, which is the tunneling of actually Cooper pairs. Cooper pairs, you may be knowing, that is the Cooper pairs are paired electron systems in which is being seen in superconductors. So So those Cooper pairs get transferred from one superconductor to the other one via the channel of this insulator. And this is actually, if I try to connect it with whatever you are learning now, is actually the quantum potential barrier problem. Okay, so quantum potential barrier problem. I hope that you have learned it, right? Okay, first of all, let me tell you, if I am not clear to you, I'll be okay that you stop me and then ask me doubts and all. I just want to make sure that we are all in the same page also, okay? Even though I don't mind, masters, just annoy me. I'm not hearing anything. Okay. Okay, cool. This superconductor insulator superconductor Josephson junction system, it is a replica of quantum potential well problem. So just learn it, like how these electrons, which has got Cooper pairs actually, which are paired electrons, which has energy less than the potential energy, the barrier, which is the barrier potential is that corresponding to the insulator here. And those electrons get transferred from one superconducting system to the other superconducting system. So that principle is being especially made applicable in our systems, which is based on qubits. And this is one of the image, scan electron microscope image, which you see, which we have fabricated in our lab. And you see that, from the, you see my mouse, right? Hello?
Yes.
Great. Okay. So
Yes,
you can see, great. So you can see that, this Cooper pair, I'm sorry, you can see that the dimension here is 5 micrometers. So you can imagine this much is 5 micrometer. Okay. So you can imagine how difficult the process of fabrication of these kind of systems are. So I hope that you may be clear about, you might have understood what I'm basically working on, and then why actually what are qubits? Before this, I wanted to tell you the qubits are actually another, it is actually a system which we want to make. What is this big importance of qubits? Qubits are replicas of artificial atoms. Actually, we are trying to mimic atoms, make atoms, so that atoms in lab, so that we can study that. There is a big curiosity to learn how atom interaction takes place, atom interact with the environment around. All these things are big curious interesting fields which we are really interested to work on. And qubits pay a way for it, like they are called artificial atoms. And why they are called artificial atoms? Because they are quantum harmonic oscillators. We know that atoms are harmonic oscillators. They are some kind of vibrating systems, and which we call as harmonic oscillator systems. And since these artificial atoms based on qubits are very small in nature, they start showing quantum nature as well, something which is unpredictable and probabilistic as well. So this is, the one shown in this figure here is the, energy eigenvalue, how this energy eigenvalue plot. Yeah, that is what it is shown here. And then of that of harmonic oscillators, you might have learned it, like, using this annihilation creation operators and Inaguration, and that the Hamiltonian corresponding to that is n plus half h cross omega. And that is what these are the different modes corresponding to each and every n values of those Hamiltonians. And yeah, so basically what we are doing is we are fabricating these qubits in our lab, and then these qubits, their potential well, we are trying to make it something similar to that of an atom, which is, that's why it is called artificial atoms. And then what we are trying to do is this what I have shown here is not a replica of the real atoms. What the real atoms are, these energy level differences, it will be, smaller. It will be smaller as we go up. in energy scale. So so we need manipulations of those qubits as well, and we do that by playing with the non-linearity associated with the qubits. Okay, and there are different kinds of qubits. There are flux qubits, transmon qubits, and all. All flux qubits are active when magnetic field active and more interactive with magnetic field modes. Transmon qubits are more interactive with electric field modes. All this you will understand, once you learn a little bit about, but then I don't want to scare you by telling all those things, but just understand that qubit is an artificial atom system where we are trying to mimic the potential well corresponding to that of the atom, normal atoms. And then we are trying to manipulate these systems by playing with the non-linearity associated with these Josephson superconducting Josephson junctions qubits. So yeah, so that's what this slide is about. And then what is the aim of all? As I already told you, it's about whatever, if we will be able to learn these qubits, the atom-atom interaction and all these things, and we will be able to control this single qubit systems. And one of the means is what I have done in my lab previously in Technion, Israel. And Technion is an institute similar to Indian Institute of Technology in Israel. And then there what I have done is, so I told you that qubits, we are trying to manipulate this quantum well kind of behavior, manipulate this potential well, right? We want to make it more anharmonic in nature. What I meant by anharmonic is we need to make it more asymmetric. This looks like very much symmetric to x is equal to 0 line, right? But that's not the actual case. For the real atoms, this potential well, which I'm showing you here, is anharmonic. It is not symmetric with respect to x is equal to 0, and also these energy levels becomes very much discrete. It's discrete as well. It's here discrete also, but then it is more. It becomes more and more like continuum as the energy goes up. So so that's why playing with the non-linearities. And one another thing which I have studied with these qubits are qubit magnet interaction, tiny magnet interaction. So that is what I would like to show some of my results to you, so that again, I will not go deep into the technicalities, but then just give you a glance about it. And this is what I've studied in our lab. We made a qubit, and then we tried to couple it with a spin system. Okay, so the sole purpose of that, this thing which I have shown you is a representation of coupling. So qubit is getting coupled with a spin system. And what is the motivation of this? What we see is whatever qubit systems we are making in the labs, they are actually they do not stay in this perfect potential well kind of arrangement for long. They are always susceptible to Bath interactions. What I meant by Bath interactions, please stop me if I am not making sense to you. Okay, what I meant by Bath interaction is the interaction of these qubit systems with the environment is inducing noise into the system, because of which this potential well will no longer be a potential well. So it will be something else. Okay, so but we don't want that to happen. What we need is, we want that that potential well to be intact, but then that will be intact only for a few microseconds time, which is not a good thing. So we call in technical terms coherence of that system. Okay, the coherence time of that system is only few microseconds, which is not a good thing. So what we do is, within that few microsecond limit of time, we try to interact that qubit system with with a more stable coherent system, which is a spin system. Okay, spin system based on Ferrimagnetic sphere. So the coherence time of that ferrimagnetic sphere systems is of the order of milliseconds. And so we are trying to basically couple a relatively unstable system with a stable system, so that by meantime of this microsecond, within that time scale, we will be able to transfer whatever information we can gather from this qubit to this more stable spin system. And this spin systems, millisecond order, amazing. We have a lot of detectors which can gather information from this system, which can gather information within this millisecond time scale. So that is the advantage of coupling, advantage of this project, and that is what I have been trying to do. And first, the sole purpose was to understand this system, and this will not happen in an open environment. Okay, this has to be these two couple system itself has to be in a confined environment of a cavity. That is what electromagnetic mode cavity. So that is what we have to do. So that those electromagnetic mode inside that cavity, that will be acting as a mediator between these two guys, and those modes itself will be used for readout. We will extract the information from those electromagnetic modes, and will be able to study those things in the study those signals in the detector. So so for all these things to happen, one of the important factors is this qubit spin system should have strong coupling. And this strong coupling, we have equations corresponding to that. The term, the real technical term for it is, we have some like your Lorentz oscillator problem, which we have studied in electrodynamics. This model is called Jaynes-Cumming model, which you will study in quantum optics actually. So there, this coupling factor G comes into picture, and if this G value, if it falls in between if G by omega being the resonance, the resonance of qubit, which is going to be equal to the spin at some point of time, if we tune it, and then when that G by omega factor falls in this range, then we call it as ultra strong coupling regime, and then that's a very favorable environment for extract as much of information from the qubit to the spin, and later on from the spin to this readout detector units. So yeah, I think I don't need to tell you that about this thing. Yeah, so this is what I am showing you. This qubit is interacting with the spin, and then with the amazing G value, with falling in the ultra strong coupling regime, and with my kind of spin system, which is that of made of ferrimagnetic material. We had a coupling falling in the ultra strong coupling regime, and we were able to read it out optically, as well as optically in the visible wavelength range, and not in the visible, actually telecom wavelength range, and then also with the microwave, also in the microwave frequency range. We were able to read it out, the information from the spin in those frequency range in the electromagnetic spectrum. So so maybe that gave you this might have given you a little bit of idea about what I am all about. I was doing all about in Technion actually. Right now I'm in another institute, but then yes, I recently only moved. So yes, so these are the ferrimagnetic spheres which we work with, and these are spheres which is of 250 micrometer diameter and all. So very small spheres, tiny magnets. We try to interact, make these tiny magnets come in contact with the qubits, and then have a crosstalk between them, and then we learn then we do the detection. So why this egg? We cannot, it's not like we can make any magnet come in contact with this qubit and then extract information out of the qubit. It's not possible. we have this magnet which we are going to use have to follow certain rules and regulations and everything. That's what this slide is all about, which I want to show you what is the importance of this spheres. So ferrimagnetic spheres, this is being learned in your level, in my master's level, also master's in physics level as well. Like ferrimagnetic spheres has spin magnetic moments aligned in this fashion, like, you know, and aligned like spin up, spin down, spin down. So this is one spin domain which I am talking about. So this alignment happens in ferrimagnetic spheres, and then it is natural in nature, and they have amazing, great, strong coupling. You know, exchange. It's called exchange coupling. Actually, this exchange coupling between these spin magnetic moments are still so strong that they act as permanent magnets. And then, I was going back. Okay. And another importance of this spin system is, once we perturb the spin system, this ferrimagnetic anti, you know, parallel spin magnetic moment system to an external magnetic field B, you know, we know that the Hamiltonian of interaction Hamiltonian mu dot B takes place, right? You will also be knowing that. And then mu dot B is the interaction Hamiltonian here. And then once that takes place, what happens is these individual spins, which has got a very good exchange coupling value, they get, you know, they undergo a slight change in their the spins tilt a little bit with respect to the applied magnetic field, and those spins tilt something in this fashion that there itself is a, you know, another giant magnetic spin is being formed over there, and giant magnetic spin wave is formed. Actually, that's what I have shown it in this green contour here. And then the giant magnetic spin, which has the spin quantum number value, which is h cross by 2. Okay, so those giant magnetic spins, that is the importance of this kind of ferrimagnetic material, and we call those giant magnetic spin waves as magnons. And yeah, you know that, you know, so this is what we have wanted to show is the Larmor precision. Omega is the Larmor precision of the Larmor frequency of these spin systems and all. But yeah, so giant magnetic spins, I understand. I feel like we are in the same page. You understand what is magnons all about, probably. And now, so this giant magnetic, these magnons, this giant magnetic spin systems is what is giving this coherence time, like, you know, in millisecond order, like, you know, that kind of value. This spin quantum spin wave is responsible for that. Okay, so okay, another important properties of this X sphere, like, you know, X sphere is the ferrimagnetic sphere based on garnet, which I have been using. And another important properties of this X sphere is, when we subjected these spheres to microwave AC magnetic field, it has some property which is called ferrimagnetic resonance. Okay, it shows ferrimagnetic resonance, and those ferrimagnetic resonance, the line width corresponding to that is of the order of kilohertz. That's why kilohertz. So this line width is inversely proportional to the coherence time as well. So this line width, what we get in ferrimagnetic resonance of this X sphere, it falls in kilohertz regime, and that is in milliseconds. So that's why we get an amazing coherence time. And then also because of the magnetic anisotropy. Magnetic anisotropy means in different directions, in X, Y, Z directions, the spin magnetic moment alignment is different. Okay, and that is what is meant by magnetic anisotropy, which is represented by susceptible magnetic susceptibility, and all those vectors come into picture there. Tensor products, tensor values comes, the tensor matrix comes into picture there, and those magnetic anisotropy is responsible for one kind of non-linearity associated with this ferrimagnetic sphere, which is called Kerr non-linearity. So Kerr non-linearity, about that, I want to tell you that, you know, this Kerr non-linear. So I already told you that What we are doing in our lab is basically making atoms, and these atoms are harmonic oscillators, artificial atoms, and these artificial atoms are quantum harmonic oscillators, and we are trying to make this quantum harmonic oscillator interact with another oscillator, another harmonic oscillator. And Ig is one of the oscillator we are dealing with, and these Igs, I just forget what I was trying to tell you. Okay. So these oscillators, these harmonic oscillators, we know that the equation corresponding to that, you might have learned it in your class, like, it is mx dot. So F is equal to ma, that is Newton's second law, right? So F is equal to ma, which is mx double dot. So if it is mx double dot plus omega squared x, that is what the linear harmonic oscillator is equal to 0. That is what the equation of the linear harmonic oscillator is. And once this, higher order terms of x comes into picture, like x cube, and then driven, all these things brings about the nonlinearity associated with those harmonic oscillators. Okay, and Kern nonlinearity is something in classical analogy, if I want to say, then it is something related to that x cube factor in that equation of harmonic oscillators. Okay, and in terms of creation annihilation operators, it is actually represented as a dagger, a dagger, a dagger, a, like that, which means there are which means it's actually a 2-photon process. All these things, I know that I may be confusing you a lot, but then you just understand that when there is only a dagger a, that means only one photon absorption. When it comes like a dagger a kind of thing, only one photon process takes place. One photon goes from the ground state to the excited state, and then that gets de-excited. These kind of systems are associated with a dagger a kind of equations, and when it comes when the system becomes a dagger a kind of the square form of it, or higher order terms of that, then means that much number of photons are undergoing these kind of ground state excited state transitions, the Fermi golden rule. Okay, yeah, those transitions are not okay. So so that's the importance of this X sphere. So this is actually the microwave properties of that These X spheres are very active in microwave regime, as well as they are a very good candidate in the telecom frequency range as well. So whatever I told you, the ferrimagnetic resonance, the Kern nonlinearity, everything is corresponding to the microwave frequency range. Like these are the properties of this X sphere in the microwave frequency range. But in they are amazing systems for in the optical frequency range as well. Okay, so these X spheres, these ferrimagnetic materials, they are used as Faraday rotators. They are components of Faraday rotators. What is called Faraday rotator? I will tell you one of the applications of Faraday rotator. Like if you try to interact these Faraday rotators with a light which has a defined polarization, like linear polarization, say light polarized in the x direction, then if you interact those light, that polarized light, with this Faraday rotator, according to the rotation which we can define and tune with some external parameter, we will be able to manipulate the polarization of the interacting light, or interacting spin systems of any things which has got directional properties of that order. So that is what the properties of that is what the implication of Faraday rotators are. And for Faraday rotators to be good, it is important that there is some constant called Verdet constant, and those constants should be a very good value. If that is a very good relatively higher value, then those materials can be a very serious good candidate for Faraday rotators, and it is such a material. It has got a Faraday Verdet constant of 304 radians per meter, and yeah, and also it has got high refractive index. Why refractive index? High refractive index is a very important property here. Is because of this high refractive index, you might, you know, right, this total internal reflection and everything which takes place, you know, we'll be able, what happens is like, you know, total internal reflection, light goes from a denser medium to a rarer medium. So denser medium in the sense the refractive index is higher than the surrounding medium there, and then that medium because of this no light going from the denser medium to the rarer medium, because of this change in, you know, higher refractive index being higher than the air medium there, that light will be undergoing total internal reflection, and this total internal reflection will help the light to get confined inside that system. It will not be leaking outside. There are leakages like evanescent waves, but that leakage is very negligible. Okay, so that is what is the one of the importance of having a system with a high refractive index, and Cijy is such a material, and that is important for the photon confinement within the system. Okay, so that's why it is a very serious and amazing candidate for so that we can couple it with qubits. And so why? Because it is active in microwave. It is a very serious candidate for microwave frequency range, and it is a very serious candidate for telecom frequency range. And if we will be, and qubit is a artificial atom which will be active only with microwave frequency range. Okay, that is something which I needed to tell you. I forget. I'm sorry. And qubit is some system which is active only in microwave frequency range. And the sole purpose of, you know, one of the important purposes of coupling this qubit with Cijy is we can so that we can have a optical readout. Like, you know, Cijy is a good material in the optical region, and we can extract information using optical detectors and all, using Cijy. Also using Cijy, the informations of qubits can be extracted out. So that is the purpose. Okay. Yeah, okay, now you understand what is the purpose of all this. You know, now what I have done in the lab is, like, you know, to understand how the Cijy system itself can be manipulated when different kind of frequency mixing and everything process, all the mixing process takes place and all. And I don't want to, you know, discuss that with you elaborately here, because that's there is a lot of technicalities there. I will just show you some of the equations which I find interesting and important, and I will show you what maybe that will help you, like, you know, to give a perspective about what is going on. So what I have done is, you know, I try to interact. What I've done is I've tried to interact with this ferrimagnetic sphere with, you know, microwave antenna and RF antennas. That means radio frequencies and microwave frequencies. Some kind of frequency mixing process we were trying making. We were trying to do that with this Cijy sphere, and then yeah, you can see that it is all placed in a magnetic field, in a DC magnetic field. So when, as I told you, when this ferrimagnetic sphere is placed in a DC magnetic field, all the spins will align in such a way that there will be a generation of giant magnetic spin waves, which are called magnons, and those magnons are allowed to interact with this DC magnetic field, AC magnetic field in the microwave frequency range as well as in the RF frequency range in this fashion. And then once that happens, you know, this is what we see, you know, the one above. This is the experimental, you know, some kind of a frequency, frequency Coombs generate, as we already know, like, you know, there is a cos omega 1 plus b cos omega 2t. Like those kind of equations leads to omega 1 plus omega t, omega 1 minus omega t, and higher order terms of all those things. Once non-linearity, all those things is what you see here. Okay, which when you do the math you will understand. I don't want, it's okay. But then you just you know, see the beauty of this this equation first. I just want to show you, like, you know, this is what is called block equation, and you know, this block equation. So while you study in your field now, whatever, in masters in physics, you're studying, you're going through all these equations of, motions and all these things. While you study all those things, please give a little bit attention, and you try to derive all these equations. These equations plays a very big role in, uh, in seeing all these amazing things which we see in the lab, and later on it will help you for your, if you are pursuing with a career in whatever field I am in quantum engineering. So so this is one kind of equations where you see that, see the time evolution of the spin polarization. Okay, spin polarization of the ferrimagnetic spins here, and then P is the spin polarization. Okay, d by dt means time evolution of that, and then that cross with omega. All these equations you will be able to get it from the basic textbooks and all. Okay, study it, understand those equations, and then plug. What I've done is, like, what I've done is trying to interact with the transverse frequency component, which is the microwave component. Transverse, okay, transverse component in this direction. Transverse means perpendicular to the direction of this DC magnetic field. That is the transference component of it, which has, you see that there is a frequency omega corresponding to that, and then there is a longitudinal component, which is that corresponding to this RF frequency. And all these things are incorporated in this omega thing, and then that is being plugged into this equation, which is the Bloch's equation. And then there is a damping factor as well, because in real life there is always damping, which is the velocity dependent quantity, right? So this damping factors are also involved, put into the plugged into this Bloch's equations. And what you see is, like, later on when you work out, plug everything out, and then you see that the time evolution, at a particular time t, that becomes, that gets a value something similar to this, something equivalent to this. So here, here you see that there is this, I think this is called zeta. Zeta is have a Bessel kind of, Bessel function kind of evolution, so the what we understand is from here. So what I want you to do is, even in your, level, master's physics level, you might have come across these kind of equations, like, and you might have, you just try to, play with these things with different kind of, systems like this and this, and this you will be able to understand by following some kind of articles, journals and all. You can follow some articles and what they have done. Example, for these are all published in my articles as these are all published. These are all published and in my name also, and you can go through those papers and you can understand while plugging it, and try to solve these equations, try to come to this line, okay, wherever, so that you can see that, so that you will get the confidence that you are able to evolve this, understand the evolution of this spin polarization. And then, so what I have done later is, this is the theoretical formula. This is how, this is the theoretical thing. This is this equation represented. So you see that there is omega 1, all those things are the x and y components of this unit here. So so try to do that, and this I have done in MATLAB. Okay, so that is what you are supposed to do. Get some equations, try to plot it in MATLAB, and try to get an understanding about it, and play with some of the parameters there, and try to understand with this parameter, okay, this is happening. Maybe this side frequency, subside bands, everything will get converged, or getting elongated. All these things you understand. Discuss that with your teachers, and with whoever you feel like comfortable with, and all. You will be knowing these kind of topics and all. And that's what I want you to do, and you can do that in this level as well. So yeah, I don't want to go too much into the technicalities of all this as well. But then I just want to show you here, like, the equations which we deal with. This equation you are currently studying in your master's in physics level as well. Like, you see here, there is this mx double dot, plus 2b x dot. This is actually equation of a harmonic oscillator, where this x dot component is the damping component, the velocity component, and x dot cube, the damping, non-linear damping also takes place. Okay, in real systems, all these things, real systems contains these parameters, x dot cube also, non-linear damping rate, and then there is this frequency component, which is omega squared x, right? And then non-linear curve equations. All this is, have an understanding about these equations, try to solve for x in these equations, try to get the Hamiltonian corresponding to these equations, okay? And then use plug those equations, try to see the time evolution of the systems, Heisenberg equation of motion. You are studying it in your quantum mechanics. Try to plug those things, those Hamiltonians, where A is an operator and H is a Hamiltonian corresponding to that, and all these things. That led me to understand what is the time evolution of a Magnon state. Like, all these things you can do it in your level also. I was simply trying to, go back to my master's level textbooks, and then, I was trying to study everything and then go through everything and equation solving and everything. So that's how you proceed. And even at this point, this level, I am also doing it. So yeah. I don't want to go through this because this is something to do with nonlinear dynamics, because I already told you that we are basically in qubit systems playing with the nonlinear associated with the systems so that we can manipulate. And also in our field, it is important that you should you should be well versed with nonlinear dynamics as well, where the statistical physics and everything comes into picture. So no, I will not discuss this. Okay. Maybe this, I think I should discuss. Okay. So here, what am I okay with the time here? Like, am I crossing the time?
Yeah, okay. You're okay with the time, huh? Continue.
Okay. Please stop me once,
Yeah,
I'll be okay with that. Okay, so I wanna tell you, like, this also you will be able to understand, like, I think what I show you here is, I told you that I wanted to my basic purpose, so aim was to couple this qubit system with these spheres, ferrimagnetic spheres, but then the mediator between those two people is the cavity mode, like electromagnetic modes in a cavity. So I used something called loop gap resonator cavity. Like this is the cavity looks like. This is how it looks like. Okay, it's actually a cylinder made of metal, aluminum actually, and it has a a gap here. Okay, the one shown in purple color, right? The one shown in purple color here is the gap there, where we have incorporated this sapphire substrate of that much low thickness, which is of 360 micrometer 360 micrometer thickness. That we made it, put it in the system. I think these things you can even make in your labs also. Like it's so easy to fabricate as well. If you have CNC systems, CNC, proper, it's important that your surface should be very smooth and good and all. These resonators you can definitely make, microwave resonators. So so loop gap resonators, and I was studying how this interaction of the cavity modes in the sense electromagnetic modes in the cavity. So this is what what I show you here is the magnetic field density, magnetic field modes which is propagating inside this cavity, and then those modes after interaction with the sphere, this is how it evolves. And these are all being done with some kind of software which follows finite elemental method kind. That also I think you can in your level you can adopt, like the softwares, and the name of the softwares is called for our HFSs, are one of the softwares. CSC is another software. Then there is Sonnet, and all these softwares you can you just try to talk to your teachers and try to or go to your nearby, institute, something amazing institutes like IISCs or TIFR. All these places you can visit, and you can, get access to these softwares and try to understand all this. So how to operate those, how to work on that software, work with those softwares. So those softwares you will be able to, we cannot evaluate it out analytically, okay? It's very difficult because it's such a huge system. If it is a very small system, something like dipole, only small, simple systems, we can do it analytically also. And I will suggest you to do that in your current level also. But then once the system becomes more and more bigger, macroscopic in order, it is recommended to be, use these kind of softwares, and which make you understand how the time evolution of how the evolution of magnetic modes happens here. And then this is how the magnetic modes, and this figure, I don't think that okay, you need not understand this for the time being. It's fine. It is basically it is basically the frequency exchange which is happening, the energy exchange which is happening between this ferrimagnetic sphere resonator and the cavity modes, which is being shown here in experimental thing. And yeah, there are certain equations and all which you have to follow, the James Cumming model and everything which I was talking about, that you will study later, like, it's okay. And should I tell about this? I think no, because this is a lot to do with nonlinear dynamics of this equation. This is basically, I'll just tell you a glimpse about it. It is basically, what is happening is we try to, so there is this X sphere. There is this X sphere in the cavity, right? So and this cavity has been driven by microwave photons. We have microwave antennas here, and then we are driving that cavity with these microwave photons. And those cavity photons, we increase the power of those microwave photons, incident photons, and that increases the Kern nonlinearity, that X cube component associated with the X sphere, and that makes the drives the X sphere to undergo some kind of phase transition. That means, okay, phase transition. Okay, I should tell you one thing, like, these ferrimagnetic spheres and all, any magnetic systems, permanent magnetic systems, they have something called Curie temperature, right? Curie temperature is the temperature which is above Curie temperature, the system. So that is what is been shown here. Is there a temperature? Is TC. TC is the Curie temperature here, okay? And once this magnetic system, this ferromagnetic system, once it becomes crosses that TC, once it becomes more than TC, the temperature corresponding to once it is put in an environment with temperature greater than TC, that ferromagnetic material becomes a paramagnet. So, and basically what happens is that spin system, some kind of spin phase transitions happens, and that happens at Curie temperature, and the corresponding magnetic field also with magnetic field, by driving this kind of ferromagnets with powerful magnets, that also can change the spin alignment of the system. And then the transition where it happens is called transition of the phase. That is transition of this ferromagnetic system to paramagnetic unit. The phase transition point is called, critical point is called Curie magnetic field, HC. So basically, we were in the lab. What we were trying to do was, like, we were trying to, this is the region we were working on in our lab, and then what happened is we tried to drive the temperature. We tried to put more and more microwave photons into the cavity and pump this X sphere to that level that it will go to this phase, this transition region, which is region 2, defined as region 2 here. And then once that phase transition happens, that is the transition from the ferromagnet to the paramagnetic system unit. Once that happens, you see some kind of non-linear phenomenon which is called chaos. And that is what is been shown here, like, as subside bands. Like when once chaos happens, you see that in the detector as this kind of subside bands. If nothing is there, if no chaos happens, there will be only one frequency, okay? Only the driving, you will see only the driving frequency in the x-axis. X-axis is the driving frequency, okay? And the y-axis is the intensity corresponding to whatever you are detecting. So we are driving the X-sphere with microwave photons, and if it is driven, if it is not a strong pumping, we will only see one frequency component. I'm sorry. Okay. So if there is only if there is no strong microwave photon driving happening, then there will be only one frequency component. But if there is too many photons, we are driving it, strong pumping is happening, we will see these kind of subside bands. And then, yeah, that's what you should understand from this figure. Only understand this figure for the time being now, okay? Yes. Okay. I think that comes to the conclusion of my talk. I don't want to, scare you a lot by, telling a lot of things. But then, what you should do in your current level, like, what you should do is, that is what I have incorporated in this slide, and that is the stuffs to be studied thoroughly for understanding quantum world and my research field. And that, only a few has been mentioned here. There are a lot, but then, you have dealt with classical harmonic oscillator problems, right? Like, Lagrangian, the Hamiltonian, solve all those equations, and with friends together, everyone together, and you disturb your teachers also properly, like, make them do hard work too, and then study and solve all those equations and understand, and plot it with MATLAB or Python. Python is, it's a free software now, and you can make use of. You should make use of it. Tell your father, Roshan's brother, tell him to buy that, and then by whatever, get the access of all this Python or MATLAB or of any of those kind, and get and plot those equations in lab, okay, and play with those parameters, whatever you have in there, and understand about, and then discuss that in this kind of PhySeekSee, organizations. That is what it is meant for, play with these, be together, help together, learn together. That is one of the importance of knowledge. Once you share, it will only grow. That's the importance of knowledge. So you do that. You be all of them. You be a big fraternity, join together, have solve those equations, study physics. It's going to be an amazing thing. Okay, you will be having so much fun with it. So do it together, and that will be more fun. And then Lagrangian Hamiltonian, okay, and then spin systems that spin, yeah, it. And then Maxwell's equations. Oh God, this Maxwell guy, like, only with those four set of equations, he was able to, predict a lot of things which is happening in the universe. It's amazing set of beautiful four equations. He was able to confine it, and that is what these string theorists and all, they have been trying to do, so that we can have a fundamental one equation to define the whole universe. That's the theory of everything, which is talking all about, right? I forget the name of the scientist. Do you remember, brother? Stephen Hawking. Yes, Stephen Hawking. His sole purpose was to do that, so that there is one equation correspondence, so that we can incorporate everything related to the universe to one confined equation. So, yeah, this Maxwell, he was able to bring forward four equations to us to explain everything, each and everything about electromagnetic field, electromagnetic dynamics and all. Hats off to that guy. And then next, and study about it and enjoy the beauty of it. Okay, that is what you should do, and discuss that with your friends. And then next is dipoles. Dipoles is a very important thing, which every time I used to go back and forth to understand my dipole interaction, multipole interaction, these things. Why? Because I'm dealing with harmonic oscillators and harmonic oscillator interactions, and all these things plays a big role. So study David Griffiths. I will tell you to do, thoroughly study, make proper notes, and yeah, keep those notes. I will suggest you to buy an iPad also, so that you can have a corporate, software not soft copy of that. Okay, so next thing is waveguides. Study how these cavity electromagnetic modes evolve, modes propagate in waveguides and all these things you will be able to study properly with POSAR. That you can do that in this level as well. Then oscillators, LCR oscillators, these are also very, very important. Why? In my field, okay? Because not only in my field, actually, even in biology, they are using these LCR oscillators. You know why? What they try to do is they make some biological systems, and they try to try to make the electrical equivalent circuit of those biological molecule interactions. So they're also in that field, biomedical engineering field also. They are doing all those things. They are making use of these electrical LCR oscillator problems and all. So study it perfectly well, okay? And then there is something which you are studying, in electronics, maximum power transfer theorem, the impedance matching condition. Oh God, this thing, I found it very, very useful and very, very important also. If once I do not get this oscillator interaction impedance mismatch, once I get that mismatching, I see that systems doesn't work perfectly at all. So for that, you need to properly evaluate the corresponding impedance values and everything. All those things are important, and do that at your level now, okay? And then yes, quantum mechanics. All basically everything whatever I'm studying is quantum mechanical in nature, quantum qubits, quantum computation, quantum information science, all these things, quantum physicists. And so definitely one-dimensional potential problems, WKD approximations, perturbation theory, Stark effects, Zeeman effects, whatever I told you now, I'm trying to interact this qubit, which is an artificial atom, with a tiny magnet, right? So tiny magnet that introduces Zeeman effect into the system, because of which the energy level splitting takes place. All those things happens, right? So it's important that you study the equations, and not only study those equations, but try to read some articles corresponding to those, these kind of interactions, and then try to deduce those whatever plot they have been showing in that article. Try to deduce those in your all these things you can do in your level as well. And then yeah, plotting up. This is one of the simple thing which I enjoyed when the very first time once I started physics. This is one thing which made me feel like wow, something is obeying whatever I studied and used to, with the equations and all. I was able to replicate it in the real, experimental values. So plotting absorption spectrum from Lorentz oscillator problem. Lorentz oscillator is something which you are studying right now. Lorentz oscillator, what is it like? It's dipole electric field interaction, D dot E. And from that D dot E, you will be able to plot, you will be able to bring this, you will be able to get this refractive index value, the absorption coefficient value, all these things you will be able to deduce. And try to plot that in MATLAB, and then fit it with any experimental plot which you see in some kind of journals or articles. That is what you can do that in your level as well. Try to incorporate your teachers also into that. And then yes, coding with Python, MATLAB. Coding is very important in our unit. And then so on and so forth. Just tap it and enjoy it. That is what I want to tell you. And thank you for patiently listening to me. Yeah, now I think I'm done.
Yes, sir. Thank you, Cijy.
Did I make sense? Was I okay, or was I too technical?
I think it was very nice. I followed some things, not all complete, definitely.
Oh, okay. Okay.
Right.
Oh, I'm
Thank you.
sorry. I'm sorry. I was like, this is the problem, yeah. Okay.
No, it
I
was
thought
good.
I was
It was good, Cijy.
like, it is not about good or bad. It's about
No, what I mean is that it
understandable.
would, yeah, they may not understand everything because unfortunately solid state physics comes in their 4th semester.
Okay.
So
Okay.
yeah, so
Cool.
but then what I can say is you have done the groundwork for that, helping them see the perspective, putting things into perspective is what you have done for them. So hopefully they will study it well when they do it.
Thanks for
I think it was
okay.
nice.
I will appreciate questions, especially from
Yes.
kids.
Right. Thanks a lot, Dr. Cijy, for that wonderful talk. I'm sure all of us will now look up to the sky and also make sure we look down and see what's in the world of the small. I would now like to call Jalak for any questions. The audience, if you have any questions, you can either put it on the chat box or you can raise your hands and we'll ask you to unmute and you can ask your question. Jalak, you can take over for Q&A.
Yeah, thank you, Vikrant. Audience, does anyone have any question? Thank you for your talk. We are just waiting for
audience without question means oh God. I just wish that. Okay.
I think there is a question in the chat box, Jalak.
Yes, ma'am. So this question is from Vikrant, and he says, I just know vaguely that in ferromagnetic materials, the domains are aligned in the same direction, and in antiferromagnets, they are aligned in the opposite directions. From one of your starting slides, I saw the ferrimagnets also have oppositely aligned domains. So what is the major difference in brief that distinguishes between antiferromagnets and ferrimagnets?
Okay. Nice question. Who told it? Like, who asked it actually?
Vikrant.
Vikrant. Nice question, Vikrant. Actually, so these magnetic systems, paramagnetic, ferrimagnetic, permanent magnets, and everything systems, all these things are defined by something called exchange coupling, long range interactions. So exchange coupling is a parameter, is the main parameter. Okay. So basically, what is exchange coupling? It's a spin-spin interaction which is happening among the in between the spin magnetic moments here with the systems, and those values are different for different materials, and that according to that values, if it's a very big value, that exchange coupling parameter is very high, then we call it permanent magnets or ferrimagnetic systems, and if it's low, it will not be having that, it will not have perfect alignment kind of systems. And to answer you, like, ferrimagnetic and antiferromagnetic, and again, what is happening there is spin-spin interaction, right? And because of those, interactions, Hamiltonian interactions, this neighboring spins allows the other spin to align in the same direction. For in the case of ferrimagnetic, ferromagnetic thing, and so basically, exchange coupling is the main reason for this kind of alignments between the spin domains. I hope that I answered it. Did I?
Yes, ma'am. Thank you. I think that does distinguish between antiferromagnets and ferrimagnets.
Okay, somebody raised hand. Arun.
Arun, sir, you can go ahead.
Yeah. So my question is, so for these nano-sized ferrimagnets, the big spheres that you have said, what is the typical Curie temperature like?
Okay. So the Curie temperature for this garnet-based spheres is 590. Actually, 590 or 490 Kelvin. I think 570 Kelvin. Yeah, it's 570 Kelvin. Okay, that is also another important aspects of this ferrimagnet, that it needs a very high temperature to change its phase, to undergo phase transition. So yeah, that is
So which means that
relevant.
even at room temperature, they will be.
Yeah, it's a very good
Yeah.
magnet at room temperature, and we can work this system with, at room temperature like perfectly well, no problem. Mhm.
Does the audience have any other question?
Yeah. So Cijy, since
Yes, Parul?
yeah, you are talking of superconducting magnets, right? You are talking of superconducting materials and Josephson junctions. So you
Yes.
must be working at low temperatures, right?
Okay, I didn't mention you that, right? Yeah, obviously. So superconductors are those materials which, below a certain temperature only it acts as superconductors. Otherwise, there are, or below a certain temperature only there will be Cooper pairs. The electron pairs happen. Okay, above that temperature, it will be just normal metal. And yes, that was the question, right?
Yeah. So what kind of refrigerators do you use?
For qubits to work,
Yeah.
the temperature which we use is 20 millikelvin. In our lab, it's 20 millikelvin. Can you imagine? It's very much near to absolute zero.
Yeah. So what kind of refrigerators do you use?
The refrigerators which we use is called dilution refrigerator, which has so we have helium unit. Okay, helium. You know that helium has temperature. Helium gas has temperature of 4 Kelvin, right? And then we try to compress it again. By some kind of electrical equipments and all, compressors and everything, and then we will be able to bring it down to 20 millikelvin level. That is the thing. Like that is also another technology, amazing technology by itself. Yeah.
Yeah. So I mean, I think our second years were fortunate. They have heard another student of ours, Ramya, who also works on qubits. So I think for them it is a series of second talk on qubits. So she was also working on dilution refrigerator, and I think it puts things more into perspective. We will try that if we can take our students to IISc this year. We'll probably show them a dilution refrigerator.
IISc, Professor Vibhor.
Yeah.
Yes.
So Ramya was actually working with the Professor Vibhor.
Amazing. Yes. I know. Vibhor Singh, and then I think IISc only Vibhor Singh, and then Raman Institute. I think one professor is there. But then the main guy, I think, is in TIFR, Professor Vijay. Wow. Especially with my systems and all, Professor Vijay is TIFR, okay? Tata Institute of Fundamental Research. Mm-hmm. It will be very good to work with him as well. Mm-hmm.
Thanks.
Mm-hmm.
Yeah, suppose nobody has questions, I can ask one question. Huh?
Okay, Roshan.
Yeah, say you told about coupling between Magnon and cavity modes in one of your slides. Yeah, but I didn't understand because in so I think it is in ferromagnetic materials that the properties change depending on the sign of the so I think permeability. But I don't know about ferromagnetic materials. Is it correct? I vaguely remember.
This sign of the permeability, obviously it changes according to the sign of the permeability, but it's always positive. Naturally it is very always positive in nature. Okay, but then in order to make it negative, we need to artificially do some kind of combinations, like stacks, dielectric combinations. All those things bring forth this negative mu permeability values. We cannot naturally it doesn't oppose, but stack it with dielectric stacks and all, then negative. But then in the case of this X sphere, it's positive permeability. We are not trying to manipulate those things. Yeah.
Okay. Here there is one more question. I think Vikrant can read it.
There's a question from Sanat. He says, how do you detect a bit flip in the case of qubit since it has multiple states because of superposition?
Okay, would you please repeat that question once again?
How do you detect a bit flip in case of qubits since it has multiple states because of superposition?
Okay. So qubits, what we generally try to do is like, it's a two-level systems and we need to make it as a two-level systems, okay? But that doesn't guarantee that we will not have multiple levels. So what we do is we try to make the impact of the other levels as small as possible. How? By perturbing it with frequencies, which is very similar, which very equivalent to that of the quantization energy difference between those two levels which we want to study with. So that's how we generally, and we try to reduce the other frequency component effects, some kind of suppressions, so we use some kind of filters or something of that, something like that we do in order to yeah, I think I answered your question. Did I?
Yes, ma'am. He says thank you. Is there any other question from the audience? Ma'am, thank you for your insightful talk. I'll hand over to Vikrant.
Thank you, Jalak. Dr. Cijy, I'd like to thank you again for taking out time for this wonderful talk.
Thank you.
As our ending, as we come to an end, I invite Parul ma'am to deliver the vote of thanks.
Good afternoon, everyone. So on behalf of the entire PG Physics Department, I would take this opportunity to thank our guest and speaker for today's talk, Dr. Cijy Mathai, for accepting our invitation at such a short notice and agreeing to give talk to our students. Thank you so much, Cijy.
Thank you, Parul.
So I wish you all the very best for your future endeavors.
Amazing. We wish you too. Thank you.
I would also like to express my sincere gratitude to our principal, Reverend Father Victor Lobo, our HOD, Professor Maria Sahai Raj, and the Dean of School of Physical Sciences, Professor Rabai, for their support and encouragement. I must express my heartfelt thanks to the coordinator of our PG Physics course, Dr. Arun Varma Thampan, for his constant support and guidance. Special thanks to Father Roshan for arranging a wonderful speaker for today afternoon talk. I would also like to thank Mohan and Ricky, my colleagues, for their cooperation and help. And I also extend my thanks to the students of the PhySeekSee team. I have been fortunate enough to be backed by a team of dedicated and wonderful students who take care of all the logistics and make sure that events like these run smoothly. So thank you to the entire team. And lastly, a big thanks to all the participants of today's talk. I hope the session was fruitful for you, and this seminar has sparked your curiosity and motivated you to learn more. So thank you, one and all.
I also want to take this opportunity to thank especially Roshan brother. Yeah, your father Roshan actually, and thank you all for Arun, Vikrant, everyone. Okay, and the students too. Thank you.
Yes, sir. I also would like to join the chorus of thanks already said by others. So thanks for accepting our invitation at a last minute, just about 1 week earlier. Thanks a lot, Cijy, for that. And it was very good talk. And just to tell you that we also teach Python to our students.
Great.
And many of them are, yes, and many of them are experts. And we all look up to Dr. Arun, who is very good in Python and who himself is spearheading teaching Python here. I am very happy that we have understood the importance of Python and we have already implemented it. So that is that part is taken care of by Arun sir. He himself is very good in Python. Normally for others, we say, are you comfortable with Python? But Arun sir, we always say Python is comfortable with Arun sir because he knows it very well. He's very comfortable with that. Yes, sir. So that's the point, and we would like to improve on that. So that apart, I want to thank you for inspiring us. And at the end, what you said, what you can do in a PG course by ourselves, that is very important. That is, I think, I hope our students have taken. So thanks again. I will also thank all the students and even Shivani who designed the poster, and so thanks. And Cijy liked the poster, so thanks for that. Over
I
to
like
Arun.
the poster. Thank you.
Yes.
Thank you. Thank you. And thanks for bringing up those last points. And we try to encourage them to play with equations. So and that you brought it out in your talk. Thank you very much.
Yeah. I find it very important for my whatever research I have done so far too. All the best.
Yes. So thanks again. So thanks.
Thank you.
I think I will leave now. So thanks. Yes.
Okay. Thank you. Bye-bye.
Thanks. Bye.
Thank you,
Thanks.
everyone. Thank you.